In this lecture, we're going to talk about the design of parking lots and the use of curbs. And when we're talking about the design of parking lot, there's actually a lot of important skills here for landscape architects, and it's often something that's not very well done. There are a lot of issues that we need to consider and include when designing parking lots for cars, people, as well as the environment. So as we start to think about the design of parking lots, there are a lot of things that we need to consider. And frankly, there are quite a few just when we look at cars. Because in all honesty, people are driving cars, and normally when they are running around a parking lot, it's not one of their best times where they are most attentive to things. So we need to be aware of things like, the sizes of the spaces, the layout of the spaces, the overall layout of the design, whether it's rectangular or maybe it's at 90 degrees, what sort of medians and planting islands we might have, and then of course the internal circulation of the parking lot for, where do the cars run? Are they looping around? We want to avoid dead end parking. And we also have to think about the sort of gradients that we have for different cars. And then, of course, once people get out of their cars, we have to think about them walking, their safety. What is the visual impact? Can they see? Where do we place the accessible parking spaces? All sorts of different issues with visibility, comfort, lighting, and shading. And then finally, for environmental issues, we always have to look at, stormwater and drainage. How are we going to capture and treat that water? What are the existing landforms or the ones we may want to create? Preserving existing vegetation, and of course, adding additional vegetation for the benefit of the pedestrians and frankly, to also shade the vehicles during the daytime. So to grade parking lots effectively, we want to grade them with uniform slopes. That is, we want a consistent slope across as much of the parking lot as possible. To do this, it's most effective to simply treat parking lots as a series of folded planes with longitudinal slopes and cross slopes. These combined systems form ridges and valleys that will then direct water where we want to have it directed. And as we design these systems, we want to think about how we can design this to minimize the grading that is existing on site. We want to do that in part to cut down on the cut and fill, and we also want to do that to preserve existing vegetation. And of course, we want to be thinking about the drainage and how we can direct the water either to inlets or more commonly to bioswales where the water could be filtered and recharged. And that focus on drainage is something we're going to come back to again and again. So one of the aspects of designing parking lots that is often challenging for students is how do you work with curbs? The fact is, curbs are a very important part of most parking design in urban areas. They provide a vertical separation at the road edge, and what that does is a couple of things. First off, it protects the edge of the road so that cars don't drive on the edge and thereby break up the asphalt where it's on the edge of the road. It also directs stormwater so that we can put water where we want it, and we have a couple of goals for that. Number one is normally safety. We don't want water to run where the cars are going to be driving, especially where they're going to be turning, and we want to avoid water where the pedestrians are going to be walking. And in both of these cases, it's because the water will freeze in winter and obviously become ice and becomes a safety hazard. And then, of course, the other issue is that these curbs provide a safety barrier. Basically, it provides a small barrier to keep cars from winding up on sidewalks that are supposed to be areas of safety zones just for the pedestrians. So the design of curbs can vary. We have the typical vertical curb like you see in this drawing. There are also rolled curbs that allow people to drive up onto them. There even are flat curbs that allow people to drive across them completely. But the most common type of curb we're going to be dealing with is the typical raised curb. This is normally about 6 inches high. They'll range in all honesty. Some of them are as low as 3 inches. Some of them are high as 8 inches. And that's sometimes done for issues of access, sometimes for safety, and sometimes simply because we've been adding pavement to the parking lot over the years. The combination of this curb and gutter basically create a swale along the edge of the road, and we use this to direct water where we want it to be, because one of our goals with parking lots is to get the water off the pavement as quickly as possible in sheet flow into some sort of a curb and gutter, where we can then direct it to a bioretention system of some sort or to a drain if necessary. But the main reason is we want to get the water away from where the cars drive and away from where the people will be walking. It's often easiest to think of curbs as nothing more than just small walls. Now, the fact is, curbs are not just like walls, because most walls are usually flat on the top, and curbs normally slope with the land or with the slope of the parking lot. But the idea of treating curbs as small walls makes it easier to understand how a contour may be running across the parking lot, and then it hits the face of the curb, and in plan it basically disappears. But you can imagine what that contour is actually doing, just like with a wall. It's running along the face of the curb until it gets to the top of the curb, and then it runs over onto the landscape area. So if we are to look at how contours interact with curbs, this drawing gives a pretty simplified explanation, because the contour is running across the parking lot, and then it hits the curb, it runs along the face of the curb, and then comes off the face of the curb onto the sidewalk. It's good to look at this and recognize the sort of proportions. If we have, for example, 1 foot contours, then if we have 6-inch curbs, the contour will run halfway along the curb before it jumps up and runs over on the sidewalk. So each contour will go halfway between where it hits and where the next contour hits before it jumps across the curb and onto the sidewalk. And we'll talk about this more in a little bit. It's important to be able to visualize how these contours run along curbs and also how they run along a parking lot. So this slide is being used because we have a brick wall adjacent to a parking lot with a sidewalk in between. And as you can imagine, the brick wall is simply a series of horizontal bricks stacked. And so the bricks themselves represent an even elevation running across the wall. To make this more obvious, we've added a blue line here running along the wall, and it's running with the bricks, and it represents then one line of even elevation. So you can imagine a contour line is going to run along that wall at even elevation, basically running along the same line of bricks horizontally all the way along that wall. Now, if we add a contour line at the bottom of that wall, you can then see the contour line is coming towards us along that wall. It then hits the sidewalk. It's now running across the sidewalk towards the curb, or towards the parking lot, if you will. When it hits the edge of that curb, it then runs along the face of that curb until it meets the even elevation, or the same elevation in the parking lot, and then the contour line simply runs across the parking lot. It's going to be worth your time to come back and look at this slide a few times, because this is basically a perspective representation of what you're going to be drawing in plan on your exercises and on your drawings. So this pattern of contours in a parking lot is going to repeat itself. It's going to repeat itself on a uniform slope, and this is exactly what you're going to imagine in a perspective drawing, but you're actually going to have to draw this in a plan drawing. So here we have a plan drawing of the exact same situation. We've got the 64 contour coming over where it's going to hit a 6-inch curb. It's going to run halfway along the curb towards the 63. It is then going to cross over the curb and run away from the parking lot. And because these are 6-inch curves in this drawing, you can easily imagine that the bottom of curb, where the contour crosses over on the top, is simply going to be 6 inches below. So what that means is the bottom of curb that we have located in this drawing is going to be halfway between the 63 contour and the 64 contour. And if that bottom of curb is halfway between, and you know it is a 6-inch curb, then you know the elevation at the top of the curb at that same point is going to be 64. So this is a skill you're going to use as you are designing your parking lots and getting your contours correctly drawn on them. Now, to have a parking lot properly built, we need a lot of information about these curbs. What we need to know is what is the elevation at the top of the curb and at the bottom of the curb, and we need to know this about specific locations within the parking lot. We call out the top of the curb as a TC and the bottom of the curb as a BC, and we have elevations that are different for each of these. And of course, if you have a 6-inch curb, the difference would be 0.5 feet for all of these. However, we often can group these together as a top of curb, bottom of curb, right next to each other on the drawing, and there should be a ½ foot difference, assuming that we are using 6-inch tall curbs. We have to include spot elevations for curbs at all critical locations in a parking lot. And there are a few that we're going to list right here. First off, all corners. Whether it's an inside corner or an outside corner, we must give the top of curb and the bottom of the curb. All relative high points. So in the center of this drawing, you can see a spot elevation. That is a high point where the slope is changing in one direction to another direction. All low points. So if you look in the upper left-hand corner of this, you will see a low point. In this case, it's labeled as a RIM, which means rim, or a DI, which means drop inlet. So we have to have spot elevations at all low points, rims, and drop inlets, which normally go together. And finally, we have to have spot elevations at all radius tangents. So if we have a curved line that is curved and it then becomes straight, we have to have a spot elevation where the straight portion of the curb intersects with the curved portion of the curb. So it's often very helpful to look at the construction of a parking lot to understand why we need these spot elevations and where they're going to be located. So in this example, you can see the curb is poured before the parking lot asphalt is laid. And so we have to have the correct elevations for these known by the contractor in order to get the elevations of the curbs correct. So there are quite a few places that we're going to need spot elevations, and we just went through a list of them. To begin with, we know that we need spot elevations any place there is a corner. And so we know that these corners all need spot elevations. We also know that we need spot elevations any place we have a straight line that then changes to a curved line. So all of these locations need spot elevations. And yes, there are quite a few of these that we're going to have on a parking lot. And likewise, when we go out to the roadway here, we're going to have spot elevations, again, every place that a curved line changes over to a straight line. And of course, if we had a ridge running down the middle of this parking lot that had water running off in two different directions, we would have to have additional spot elevations along that ridge line so the contractor would understand how to build this parking lot. That would be true whether it is a ridge line or a valley line. So here we have a slightly simpler example, and we know that we're going to need a spot elevation where we have a corner, where we have tangents hitting curves, where we have the top of a change in elevation, the bottom of a change in elevation, we're going to talk about those more later, or where we might have a low point where we might have water draining into some sort of retention system. So here we have example of a parking lot in plan, and we're going to talk briefly about all of these spot elevations that we're going to need. You can see we have quite a few of them on this plan. And why do we have to have all of those spot elevations for this construction? To begin with, we are talking only about the spot elevations for the curb. So we've highlighted the curb in the drawing here for you. And the spot elevations shown in yellow are where there are corners in the parking lot. The spot elevations shown in blue are where there are tangent points in the parking lot. That is, there is a straight line that is then hitting a curved line. We also are going to have to add spot elevations where we have the bottom of ramps in a parking lot and the top of ramps in the parking lot. And we'll talk about that in more detail in a later lecture. For your next assignment, we're going to ask you to grade 3 different parking lots. And we're not asking you to make any design decisions here. We have made all of these for you. We have decided what the slopes are, what the elevations are, how tall the curbs are. Your job is to determine what are the spot elevations. We've even shown you where those need to be. Determine where the contours are going to be, and then draw this up with correct spot elevation and contours properly labeled. So to start this process, we're going to point out some things that you need to know about these parking lots, and then we're going to point out some things you need to know to solve the problems. To begin with, all the parking lots are 100 feet long. The parking spaces are 18. The parking aisle is 22. The next parking space is 18. We've actually, in this case, given you all the spot elevations that you have to solve for in this exercise. We've also given you the slopes that you're going to be using. We've told you that the radius on these corners is 5 feet. And we've given you a starting point. We've given you one bottom of curb starting point, and that's where you're going to start this exercise. So you're going to start at this bottom of curb. That is where you have to start. You have no option. From there, you're going to want to solve the closest spot elevation. You've got a choice. It could be the one across the parking lot or the one running along the curb. We're going to show you how to solve both of them. For the one across the parking lot, you will simply use the slope that we've given you that runs across the parking lot. That's because this yellow line is the line of the valley or the swale that runs along the entire length of this parking lot. So if you wanted to start by solving the spot on the other side of the parking lot here on the aisle, you would simply use this slope with this distance to figure out how far above this existing spot elevation would be the new spot elevation. That is, you know H, you know the slope, and you're going to solve for V, or the vertical difference. The next spot is just a little more complicated because it requires two calculations. First, it requires a calculation out to find the spot elevation that is 5 feet away from your given spot elevation. To do that, you're going to use this slope, and you know it's 5 feet away because we've given you the radius of 5 feet. Then, once you find this spot elevation, you're going to use that to come down and find the next spot elevation right here. For that one, you're going to use this slope going back uphill at the same distance of 5 feet. And by doing that, you get the basic idea just from those two of how you can then work your way around this parking lot to figure out what these spot elevations are all the way down. You then, of course, can do the same thing on the other side, work your way down, and of course you will eventually want to cross over and check and make sure that this mathematically closes. That's the way you're going to know that you've got these spot elevations correct. This, of course, is just the first step of what you need to do for this parking lot, because the next thing you're going to have to do is figure out where the contours are going to be. To figure out where these contours are going to be, you're going to think about 3 lines running along the length of this parking lot. And just as you have learned to do when you're solving for swales, you're going to use the elevation at one end of the parking lot compared to the elevation at the other end of the parking lot using a specific slope. You can then figure out tick marks that will tell you where those contours are going to intersect that curb. You'll be doing the exact same thing along this fold line, and you'll be doing the exact same thing on the other side of the parking lot, and you may have to include other areas along the curb as well. Ideally then, what's going to happen is you're going to be able to determine where your contour lines are going to be on this parking lot surface, but that is not all you have to do, because you also have to determine where they're going to run off the edge of the parking lot once they get past the curb. So you already know how to do that, because you know that halfway between where these contours are hitting the parking lot, that is where the next contour is going to come off the parking lot. So you already know that this pattern is going to exist, and we're not pretending that what I'm drawing you is the correct answer, but you understand how that pattern is going to exist on this parking lot. So that is basically the process that you're going to go through to solve the first parking lot in this exercise. In the second part, we give you similar information. We let you know what the bottom of the curb is, we let you know where the spot elevations are that you need to solve for, and we let you know the slope going across the parking lot. It's important that you recognize in this the actual location of this line, because you're going to need that angle to solve this exercise. Note that if you're going to start at this point, you're going to have to run that angle across this parking lot the entire length to solve this. And I'm pointing this out. It will not hit that corner right there at the other end. What you will do is you will use that line to solve for every one of these spot elevations. And one of the ways that you will do that is you will recognize that any points that are at 90 degrees to that line will be the same elevation as they are on that line. So if I take this length, find that elevation, go sideways, I will then get this elevation as well. So you will use that process to solve for every one of these spot elevations going around the parking lot. And again, that process is based upon recognizing that if you have a 90-degree angle along a line, any point that is perpendicular to that will be the same elevation as you would achieve if you simply calculated directly along this line. You will discover that you're going to have to get a little creative in some of these because you might discover that the line doesn't go as far as you might want. So you're going to extend that line on out to make sure that you can get all of these spot elevations calculated using that baseline to begin with. Once you have that done, you are again going to use this line if you wish, or it could be the lines along the side, to figure out where the even contours are going to cross. And then you're going to have to get those contours drawn across this parking lot. Remembering, of course, that having them come across the parking lot is not enough. You have to run along the curb. And in this case, I'm going to highlight this is an 8-inch curb. So that means you will not be running halfway across. You'll be running a different length, and you will need to calculate what that length is that you'll need to run along that curb before you then come off of that curb with the contour lines. In the third example, we basically have the same idea set up for you with the addition of a drain inlet in the middle. A drain inlet in the middle means that all of the slopes are going towards that drain inlet. And that's an important concept when you start to figure out where the contours are going to run. But to begin with, you solve it in the exact same way. You know the starting point, the bottom of curb. You know the slope, so you can use that slope to find the next spot elevation. You know the slope running the other direction, so these two you can use to find this spot elevation. And all of these techniques are exactly the same, except that this is now where things change. So we have a slope running one direction and a slope running another direction. So when you get to this middle one, you now reverse and go uphill to get these. And then again, you use the same process to run all the way around this exercise. Again, you have a 6-inch curb in this one, not an 8-inch. So when you put your contours in and they hit the curb, you have to calculate them for a 6-inch curb. Because you have a drain inlet in the middle, it is very likely that your contours will all surround that drain inlet. That means that these contours are probably going to have a pattern of some sort that will all refer back to the drain inlet so that all the water will go into that drain inlet. Of course, these contours are still going to hit the curb somewhere, and you're going to determine where they hit the curb and how far you have to go before they jump over the curb as well. So this is a basic explanation of how you're going to solve this exercise. You need to go ahead and start this process and then submit the draft so that we can meet with you to go over the draft and make any corrections and most importantly, answer as many of your questions as we can.